So, hello everyone, welcome to the 17th lecture of the course Discrete-time Markov chains and Poisson processes. So, in last class we saw simple random walks and we saw that for simple symmetric random walk all states are recurrent, while for asymmetric simple random walk all states are transient. So, if P is equal to Q, then all states are recurrent, and if P not equal to Q, then all states are transient. So, today we will start with a new topic called stationary distributions, which is a very important topic. So, as we proceed along the topic, you will realize why I am saying that this is a very important topic. So, let us start. So, first we start with a definition. So, a row vector pi, so it is a row vector where pi I belonging to the state space of non-negative entries is said to be a stationary or an invariant measure for a Markov chain with transition probability matrix Pij if it satisfies this condition. What is it? That pi j should be equal to sum over I in S pi I Pij for all j in the state space. So, what is a stationary or an invariant measure? So, it is a row vector, right. So, and what is the length of that vector? The length of the vector is equal to the cardinality of the state space. So, if it is a finite state space, then it is a finite vector, and if it is an infinite state space, then it is an infinite vector. So, it is a row vector where each entry is non-negative, that means greater than or equal to 0, and it like each entry of that row vector should satisfy this condition, that pi j should be equal to summation I running summation over I in this belonging to the state space pi I Pij, and this should hold for all j in S, or in other words this should hold for each entry in the row vector, right. Now, when you see it in this way, it may not be completely clear, but let us see it more closely. So, suppose this is the vector. So, this is pi 1, pi 2 and so on. Say, let me for just illustration purpose, let me think of it as a finite vector. It is saying, now if you look at this, it is just saying this should be equal to pi 1 pi n times the matrix P. So, this is, so if for example, if you look at pi 1, what is it saying? That pi 1 should be sum over I belonging to S pi 1 times P1j. Sorry, so pi 1 is sum over pi I P1I. So, P1I is basic. So, so you are going this and then you are going along the, so when you, so this is the Pij, right, where the summation is over I, that means you are, so remember P is again a matrix. So, this pi j equal to sum over I belonging to S pi I Pij, if you write it in the matrix form, this just becomes pi p equal to pi. So, in the matrix notation, 1 can be written as pi p equal to pi, fine. So, just you know the matrix multiplication, right. So, that you write pi as a row vector. So, if you have to write this in the matrix form, this is just pi equal to pi times p, fine. So, in matrix notation, this condition for stationary or invariant measure becomes pi p equal to pi. So, this matrix notation is much easier to see or much easier to follow. Now, once you have pi p equal to pi, now you have pi p equal to pi. Now, say if I multiply both sides by p, then what do I get? I get pi p square equal to pi p. So, I am multiplying both sides, or left multiplying rather both sides by p. So, pi p square equal to pi p, but we again know pi p equal to pi. So, now continuing in this way, it is easy to see that for all n greater than or equal to 1, pi p to the n is equal to pi. Or in other words, so if I have to write in this way, it is true that pi j is equal to sum over I in S pi I p I j n. So, this is the entry of the nth transition matrix, right. So, pi j is equal, so it is not just, so this condition pi j equal to sum over I belonging to S pi I p I j also says that it should also satisfy pi j equal to sum over I belonging to S pi I p I j n, and the reason I have explained you here. Fine. So, this was stationary measure, but you see the title of the slide says stationary distribution. So, what is stationary distribution? So, a stationary measure pi is called a stationary distribution if the sum of the entries is equal to 1, or in other words, this pi I is actually the PMF of some discrete distribution. Fine. So, a stationary measure. So, for stationary measure, the only conditions are the entries has to be non-negative and this condition has to be satisfied, this pi j, or in matrix notation it has to be pi p equal to pi. Now, a stationary measure pi is called a stationary distribution if this additional condition is also satisfied, that the sum of the entries is equal to 1, or in other words, it is actually a probability mass function of some discrete probability distribution. Fine. Okay. So, that is the definition of a stationary distribution. Okay. Now, the question is, why am I calling it stationary? From where this terminology stationary is coming? So, this following theorem justifies the use of the terminology stationary. Now, let us see what is it saying. So, it says let Xn be a Markov chain with transition probability matrix P and initial distribution pi. Initial distribution pi means probability x0 equal to I is equal to pi I for I belonging to S, the state space. Now, if pi is a stationary distribution, that means anyway, so you know this is for this pi all entries, since this is an initial distribution, so this is a probability mass function, so all entries are non-negative, the sum is equal to 1. So, when you say that if pi is a stationary distribution, what you mean is that it also satisfies this condition that pi j equal to sum over I in S pi I p I j, or in other words pi p equal to pi. So, if the initial distribution also satisfies that condition that pi p equal to pi, or in other words, if it is a stationary distribution, then probability xn is equal to j is equal to pi j for all n greater than or equal to 0 and for all j in S. That means what? So, if you start with a stationary distribution, that means if your initial distribution is a stationary distribution, then after that for all n, the distributions of xn is also that same distribution. That is why, so it gets fixed. That is why you use the terminology, or that is the reason for using the terminology stationary, right. So, if you start from a stationary distribution, you remain there. So, if probability x0 is equal to I is pi I, where pi I is a stationary distribution, then probability xn is equal to I is also pi I for all n greater than or equal to 1. So, if you start with a stationary distribution, then you remain there, right. That is why you use this term stationary, because stationary means which does not move, or you are fixed there, right. That is why this terminology stationary. Okay. Now, the proof is pretty simple. So, we will prove by induction. So, for induction, first there is a basis step, right. So, for you need to prove it for n equal to 0, but you have already assumed that pi is an initial distribution. So, from definition probability x0 equal to j equal to pi j, because that is the definition of initial distribution. So, this condition is true for n equal to 0, that is the basis step. Now, we assume that probability xn is equal to j is equal to pi j for all j for some n, right. So, that is how induction works, right. So, there is a basis step where you prove it for n equal to 0, then you assume it for n and you prove it for n plus 1. That is how induction goes. So, we have now assumed it for n, that is the induction hypothesis. So, we are assuming that probability xn equal to j is equal to pi j. Now, by Markov, so now we want to show that probability xn plus 1 is equal to j, right. So, now by Markov property, probability xn plus 1 equal to j is nothing but, so first we use here what is called the law of total probability. So, we condition on the previous jump on the previous state. So, probability xn plus 1 equal to j given xn equal to I times probability xn equal to I, and you sum over all I in the state space. So, this is nothing but just law of total probability, fine. But now, we will use Markov property. We know that xn is a Markov chain. So, probability xn plus 1 equal to j given xn equal to I is nothing but just Pij, right, this small Pij, because that is the transition probability matrix of the Markov chain. So, this part probability xn, this is nothing but Pij, and this by induction hypothesis, since you have assumed that probability xn equal to j is pi j for all j. So, this will be equal to pi I, right. So, this should be equal to pi I. So, we get this, but now we know that pi is a stationary distribution, right. So, now from the definition of stationary distribution, this should be equal to pi j. So, hence you have shown that probability xn plus 1 equal to j is also pi j, and this is true for all j in S, right. So, that completes the proof, and so by induction we are done that probability xn is equal to j is pi j for all n greater than or equal to 0. So, again, so we for n equal to 0, it follows from the definition of initial distribution, then we assume it for n and then we prove it for n plus 1, and for that we just condition on xn, and then since this is a Markov chain, so we know what probability xn plus 1 equal to j given xn equal to I is, that is just simply given by the ijth entry of the transition probability matrix Pij, and since by induction hypothesis probability xn equal to I is pi I. So, and now finally we use the definition of stationary distribution to get that this is equal to pi j, fine. So, that completes the proof. So, if you start from a stationary distribution, you remain there, hence the terminology stationary, fine. Okay. So, now moving on. Now, the following theorem, so we prove yet another theorem about stationary distribution. The following theorem says that the limiting distribution, we will see what this limiting means, if it exists, is a stationary distribution, right. So, let us see the theorem, and again this theorem is true for when S, then when the state space is finite. So, let S be finite, or in other words we are looking at a finite state Markov chain. Suppose that for some I in S, Pijn converges to pi j as n goes to infinity for all j in S. That is why we are, so you see this pi j is a kind of a limiting distribution, because why? It is the limit of this pi ijn, that is why we are calling this as limiting, this pi j as limiting distribution. So, suppose such a limiting distribution exists. So, again we are not saying that this always exists. The statement of the theorem says that suppose such a pi j exists such that Pijn converges to pi j as n goes to infinity for all j in S, then this limiting distribution pi j is a stationary distribution, fine. And again when S is finite. So, this is important. I am not claiming this. This theorem does not claim it for S infinite. So, this is a statement about a finite state Markov chain, which says that if the limiting distribution, and what is the meaning of limiting distribution? Why the limiting distribution meaning is this thing, that there exists some I in S such that Pijn. So, this is basically the ijth entry of the nth transition probability matrix, or this is basically probability xn equal to j given x0 equal to I. If that converges to pi j for all j in S, then if I look at this vector pi j for j in S, that is a stationary distribution. Fine. So, the first thing we need to show is that, so anyway, so since each Pijn is greater than or equal to 0, so it is easy to see that pi j is greater than or equal to 0 for all j. So, the entries are non-negative. Now, we show that the sum is 1, again that is very simple. So, summation over j in S, pi j is equal to summation over j in S. Now, pi j is limit n going to infinity Pijn, but now this is a finite sum. So, I can take the limit outside. So, it becomes limit n going to infinity sum over j belonging to S Pijn, which is, now we know that this is again a probability vector, because this is a row in the nth transition probability matrix. This is the row sum of the nth transition probability matrix, and since that is a stochastic matrix, or in other words the row sum is equal to 1 for the nth transition probability matrix, we get that this is equal to 1. So, that gives us summation of pi j in S is equal to 1, and you see, like, to pull this limit out of this summation, we use the fact that this is a finite sum, because if it is an infinite sum, this pulling in or pulling out of limit is not a trivial thing. It requires technical assumptions, but since here this state space is finite, so this is a finite sum, so we can easily pull out limit or push the limit inside. So, the first the condition that summation pi j is equal to 1 is also satisfied. Now, we will have to show that pi p equal to pi. Fine. Okay. For that, again pi j is equal to limit n going to infinity Pijn, which is equal to limit n going to infinity. Now, again, so here we are basically using the Chapman-Kolmogorov equation. So, Pijn, I can write it as sum over k in S Pik to the n minus 1 times Pkj. So, this is nothing but just Chapman-Kolmogorov equation. Fine. But now, again, since this is a finite sum, I push the limit inside. So, limit n going to infinity Pik to the n minus 1, but it does not times Pkj, but it does not matter whether it is n minus 1 or n. So, if limit n going to infinity Pik n is pi k, so then limit n going to infinity Pik n minus 1 is also. So, this is just simple, like if xn goes to something as n goes to infinity, then xn minus 1 also goes to the same limit as n goes to infinity. Fine. So, this limit is equal to pi k, because that is our assumption that pi k is a limiting distribution. So, you get this is equal to sum over k in S pi k Pkj, which is precisely pi equal to pi p, right. So, we have shown all the three conditions, that all the entries are non-negative, they sum to 1, and also they satisfy this pi p equal to pi. Fine. So, we have shown that this limiting distribution, if it exists, is a stationary distribution. Fine. So, for a finite state space, this actually gives you a way of finding a stationary distribution, right. So, if you can find P, like the entries of the nth transition matrix, and you can take limit of each entry, and if the limit exists, that gives you a stationary distribution. So, this is a way of finding stationary distribution, but this is not the most easiest way, because calculating this nth, finding this Pijn is not always an easy task. So, but anyway, this is a method, whether it is a useful method or not is a different thing, but this is a method, but also it is not just a method, it is telling you that if the limiting distribution exists, it is a stationary distribution. Fine. Okay. So, now let us move ahead. Now, we will see some examples of like how to calculate stationary distribution for certain Markov chains, right. So, we start with our first example. So, consider this two-state Markov chain with transition probability matrix, this one. So, you go from 0 to 0 with probability 1 minus alpha, 0 to 1 with probability alpha, 1 to 0 with probability beta, and 1 to 1 with probability 1 minus beta. So, this is a Markov chain whose states space consists of only two states, 0 and 1, and this is the transition probability matrix. So, we will try to calculate its stationary distribution, fine. So, let pi 0, pi 1 be a stationary distribution. Now, if it has to be a stationary distribution, then it needs to satisfy. So, remember, so these are the two conditions which you get from pi p equal to pi, and this is the condition that it should sum to 1. And also, we need to find a solution where each pi I is greater than or equal to 0. But now, so this is just a simple system of equations. So, I am not solving it here, but you can solve it easily. You solve it and see that you get pi 0, you get a unique solution, pi 0 equal to beta over alpha plus beta, and pi 1 is equal to alpha over alpha plus beta, right. So, for this particular example, we see that stationary distribution exists and is unique. So, you see, given a Markov chain, a priori it is not clear that whether a stationary distribution will exist or not. That is existential question. And another question is, okay, if it exists, how many such stationary distributions can exist? So, there are two questions, one of existence and the other of uniqueness, fine. So, the first question is, given a Markov chain, whether stationary distribution exists or not, that is the first question. And the second question is, okay, if it exists, how many such stationary distributions are possible? So, for this particular example that we just saw, we saw that there exists a unique stationary distribution, fine. So, now moving ahead, now again we consider another two-state Markov chain, which is a very simple Markov chain with transition probability matrix 1 and 1 0 0 1. So, this is basically the identity matrix, right. So, again it is a very simple Markov chain. So, again there are two states, fine. So, say call those states as 0 and 1, fine. So, then again it is a very trivial kind of a Markov chain. From 0 you stay in 0 and from 1 you stay in 1. So, here both 0 and 1 are what are called absorbing states, fine. So, again this is a Markov chain. So, whenever you see a transition probability matrix, you should just try to find out, okay, how many communicating classes it has, what are those communicating classes. So, here it has basically two classes, two communicating classes, and both are recurrent, fine. So, because like both are absorbing states. So, if you start from 1, you remain at 1, or if you start from 0, you remain at 0. So, two classes, both are recurrent. But anyway, here we are interested in finding the stationary distribution, but see, since this is a identity matrix, so for any, if I take any a comma 1 minus a, where a belongs to 0, this interval 0 comma 1, then that is a stationary distribution, because this pi p equal to pi is satisfied trivially. Why? Because this is an identity matrix. So, if you multiply something with the identity matrix, you get back that. So, that is why this pi p equal to pi is trivially satisfied. So, you take any, but you also need the entries to be non-negative. So, for any, you take any vector of size of length 2, any row vector of length 2, this pi p equal to pi will be satisfied, but also you need the entries to be non-negative and they should sum to 1. So, that is why if you take any row vector of this form a comma 1 minus a, where a belongs to this closed interval 0, 1, then that is a stationary distribution. Fine. So, for this particular example, there are infinitely many stationary distributions, right. So, in the previous example, we saw that stationary distribution exists and is unique, but in the second example, we saw that again stationary distribution exists, but there are infinitely many stationary distributions. Fine. So, we saw, so these two examples tells you that it is not a very trivial matter. So, in both cases, now we will see one more example where we will see that stationary distribution does not exist. So, all three cases are actually possible, right, that it will exist and unique, exist, but infinitely many does not exist. So, all three cases are possible. Till now we have seen only two examples, one where stationary distribution exists and is unique, and second example where stationary distribution exists but there are infinitely many stationary distributions. So, let me here also mention one thing. So, you see that if there are more than one stationary distributions, so if it is not possible that there will be only finitely many stationary distributions. Why? Because say if pi 1 and pi 2 are two stationary distributions, fine. Now, if you take any convex combination, what is the meaning of convex combination? That means you take lambda pi 1 plus 1 minus, sorry, let me just rewrite this again. So, say if pi 1 and pi 2 are two stationary distributions, then if I look at lambda pi plus 1 minus lambda pi 1 plus 1 minus lambda pi 2, where lambda belongs to 0, 1. Fine. So, if pi 1, so if there exists more than one stationary distribution, and then if I take their all possible convex linear combinations, what is the meaning of convex linear combination? That means combination of this form lambda pi 1 plus 1 minus lambda pi 2 for any lambda in this closed interval 0 and 1. So, if for lambda equal to 0, it gives you pi 1, and for lambda equal to 1 it gives you pi 2, but if you take lambda in between 0 and 1 you get some different vector, and you can easily check. So, see, now it is easy to see that again the entries will be non-negative, the sum of the entries will be equal to 1, and also, so if I look at since you know the linearity of matrix multiplication, so basically what I am saying is that lambda pi 1 plus 1 minus lambda pi 2, if I multiply this with p, you can see, because see, you know how matrix multiplication works. So, this again will just become lambda pi 1 plus 1 minus lambda pi 2, just if you follow the rules of matrix multiplication, and if you also use the fact that both pi 1 and pi 2 are stationary distribution. Fine. So, either there will exist a unique stationary distribution or there will exist infinitely many stationary distributions. So, it is not possible that there will exist a finitely many stationary distributions, right. So, either it is one or infinite. Fine. And what is the reason? Because if there exists more than one, so if just there exists two, from those two you can create infinitely many just by taking convex linear combinations, as I have shown you, right. So, either there will exist, so again there are three possibilities, either there exists no stationary distribution, so 0, or there exists unique stationary distribution 1, or infinitely many 0, 1, infinity. So, finitely many stationary distributions is not possible, because if there is more than one, taking convex linear combination you can create infinitely many. Fine. Okay. So, till now I have not given you an example where stationary distribution does not exist. So, now let us move to that example. Okay. So, again see, now we consider an infinite state Markov chain. So, consider the Markov chain with the following transition diagram. P plus Q equal to 1, 0 less than P less than 1. Fine. So, again here there are two parameters P and Q, but this which sum up to 1 and P is strictly between 0 and 1. So, this gives you the transition diagram. So, from 0 you always go to 1 with probability 1, but from 1 you go to 0 with probability Q and 2 with probability P. Similarly, from 2 you go to 1 with probability P and 3 with probability Q. From 3 you go to 2 with probability Q and 4 with probability P and so on. Anyway, so this is the transition diagram. Fine. Now, let pi I be a stationary distribution. Fine. Now, if it is a stationary distribution, so it should satisfy that pi p equal to pi. Now, let us write that one by one. So, pi 0 should be equal to pi 1 times q. Fine. So, if you again, so this is an infinite transition matrix. Fine. So, basically, if you look at this, so how was it? So, it was pi j is equal to sum over, sorry, not sum over j, sum over I. So, sum over I pi I p I j, right. So, this is what? So, this is sum over all I from, see, if Pij is equal to 0, that will not contribute in the sum, right. So, this is basically sum over all I from where you can go to j. Fine. So, now let us look at here. So, 0. So, from where you can go to 0? You can go to 0 only from 1, right. So, pi 0 is equal to pi 1 times p 1 0, fine. So, which is this. So, this sum is only over those i's from where you can go to j, right. So, like from if I have to write it for 0, then you can go to 0 only from 1. So, you get pi 0 is equal to pi 1 times q. Now, pi 1 is now, if it is pi 1, now you can go to 1 from 0 and from 2. From 1 you go with probability 1 and from 2 you go with probability p. So, pi 1 is equal to pi 0 times 1 plus pi 2 times p. But pi 0 you already know is pi 1 times q. So, I replace that. So, pi 1 is equal to pi 1 times q plus pi 2 times p. Now, if this pi 1 q I bring it to this side, then what do I get? So, pi 1 times 1 minus q, right. So, if I bring it to this side, then I get pi 1 times 1 minus q, which gives me pi 1 p, but and the other thing remaining on the right hand side is pi 2 times p. But you know that p is strictly between 0 and 1. So, in other words, it is not equal to 0. So, you can cancel it and you get pi 1 equal to pi 2. Now, again similarly, if you do like this, you will actually get pi 2 equal to pi 3, pi 3 equal to pi 4, pi 4 equal to pi 5 and so on. Fine. But now you see this is not possible. Why? Because this, if everything is same, so remember this is an infinite state Markov chain. Fine. So, you forget pi 0. First just look at pi 1. So, it says that your pi 1 should be equal to pi 2 should be equal to pi 3. So, pi 1, pi 2, pi 3, everything should be same, right, and pi 0 should be equal to pi 1. But if everything is same, so remember you need summation pi I to be equal to 1, I running from 0 to, so here the state space is 0 to the set of all positive or non-negative integers. So, this should be equal to 1, but if since this all this has to be equal, then what is the problem? The problem is that, so if this sum has to be equal to 1, then what you get? Now, remember everything is same. Now, if you add a same thing, say suppose if, let us look at a general fact. So, if I am adding a same thing, say a I I running from 1 to infinity. Fine. So, in this case, if you are adding a same thing, that is equal to infinity, provided this thing is strictly greater than 0. So, that tells you all this pi 1, pi 2, pi 3, pi 4, since they are equal and they should sum, their sum should be less than or equal to 1. So, if it is anything positive, the sum will be infinity. So, they should all be equal to 0. So, that tells you that pi 1 equal to pi 2 equal, all these should be equal to 0. But if pi 1 is 0, that tells you that pi 0 is equal to 0, but then finally you end up with that all entries should be equal to 0, but even in that case the sum will not be equal to 1, because sum of zeros is 0. So, if each pi I for I equal to 1, 2 and so on, if it is positive, then the sum will be infinity. So, the sum, each entry cannot be positive. So, it has to be 0. Remember, it has to be non-negative. So, if it cannot be positive, it has to be 0. But if it is 0, then it turns out that each entry will be equal to 0. But in that case again, the sum will be 0 and not 1. So, you see in all cases, it is not possible that, so you can solve this equation, but the problem is it will not be a distribution. So, you can say, so in this way you can say that if I look at this vector of all zeros, so if I look at the vector of all zeros, that is a stationary measure. Fine. So, that is a stationary measure, but it will not be a stationary distribution, because its sum is not equal to 1. Fine. So, its sum is not equal to 1. So, it is not a stationary distribution. So, a stationary distribution. So, for this particular example, stationary distribution does not exist. Fine. So, here we have given now all three examples. An example where stationary distribution exists and is unique, an example where stationary distribution exists, but there are infinitely many stationary distributions, and a third example where there does not exist a stationary distribution. But remember, in this third example, a stationary measure exists, but you will see, like, since we are in working with probability, so we want the measure to be actually, so we want this summation pi I equal to 1 condition to hold. So, for this particular example, the stationary distribution does not exist. Fine. Okay. Now, you see, if you have noticed it, for in the first two examples, it was finite state Markov chain, and in third example, I went to an infinite state Markov chain to give an example of a Markov chain where stationary distribution does not exist. So, why didn't I give an example of a finite state Markov chain where a stationary distribution does not exist? The reason is that is actually not possible. That is our next theorem, which tells you if Xn is a Markov chain with finite state space, then there exists at least one stationary distribution. Fine. So, if Xn is a Markov chain with a finite state space, then there exists at least one stationary distribution. Fine. So, if you have a Markov chain with a finite state space, then the possibility that there does not exist a stationary distribution is not possible. So, either it will have one or infinitely many, but 0 is not a possibility. So, only when you go to an infinite state Markov chain, all three possibilities are possible, that no stationary distribution, exact unique stationary distribution, and infinitely many stationary distributions. Fine. So, for a finite state Markov chain, there always exists at least one stationary distribution. Like in example 2, we saw that uniqueness is not guaranteed. There can be infinitely many stationary distributions, but existence is guaranteed. So, for a finite state Markov chain, existence of stationary distribution is guaranteed. But if you go to infinite state Markov chain, it is possible that a stationary distribution does not exist. So, in that case, all three possibilities are true: 0, 1 as well as infinity. Fine? Okay. So, yeah. So, this is the thing, so which I was telling you. So, remember, so this is the calculation which I did in the previous part. So, that so if pi 1 is equal to C, so then pi 0 equal to CQ, and if pi 1, so all these are same. So, you get, so this sum cannot be 1. So, in this case there does not exist a stationary distribution, and if Xn is a Markov chain with finite state space, then there exists at least one stationary distribution. Fine? Okay. So, we will stop here today. Thank you all.